Good afternoon, everyone. So, in the last lecture, we discussed the delta learning rule or the learning rule, which is also called as the continuous perceptron learning rule, right? And we solved a problem on that. So, let us revise about this rule a bit. So, this particular rule, what is the weight update equation delta W? What is delta W for delta learning rule? Yes, what is the weight update for a generalized learning rule? What is the equation? General equation?
CRX.
It is CRX. So what is going to change in CRX for each learning rule?
R.
R. So tell me what is R here. So it is C times what is R in case of delta learning rule. We did a small derivation in yesterday's lecture.
Desired minus F net into derivative.
Into derivative of F, right? This is the weight update equation for delta learning. Now we saw two different activation functions which we usually consider are the bipolar sigmoid and the unipolar sigmoid, right? So for bipolar sigmoid, what is f dash net? This also we derived yesterday. What is f dash net? What is the derivative in terms of the output? So if O is the output, what is O? O is nothing but f of net, right? The activation function applied to the net value, right? So what is f dash net in case of bipolar sigmoid? Do you recollect? Half into 1 minus O square. Remember, left hand side equal to right hand side, where we found out the derivative and we proved somehow that this equals this, right? Half 1 minus O square. And in the case of unipolar sigmoid, which I left to you as an exercise, what is f dash net? F dash net is nothing but O into 1 minus O. Okay, so these were the concepts that we discussed in the last lecture. So we saw the learning signal for the delta learning rule, how using gradient descent by minimization of squared error, we found out the expression for R, the learning signal. And then we also established this relationship, this and this one, that is expressing the derivative in terms of the output. Okay. And then we solved one particular problem on this. Okay. So this was what we did yesterday. So we'll move ahead. We'll solve one more smaller problem on delta learning today. Okay. And I want response from your side. Then we look at the SCPTA algorithm, which is the single continuous perceptron training algorithm. Continuous perceptron means delta, right? So delta learning algorithm we will look at. Then we will look at other learning rules, that is Widrow, Hoff, and correlation learning. Okay, so two more rules we look at. So that is what we're going to discuss today. So this is the next problem. So there are two input patterns given to you, and you have to use delta learning rule using C is 0.25. Okay. And initial weights are also given. Desired outputs are given. The training pairs are given. Okay. What is missing here?
Activation function.
Yes, activation function. So we see, as far as we are concerned, we have only two possible activation functions for this. An activation function that you're going to use, if d is given like this, -1 and +1, then you go for the activation which has a range -1 to +1. And which is that?
Bipolar.
Bipolar sigmoid. Okay. So that is what you're going to use. So we'll solve it, but I want responses from you, please. This time I want everyone to solve. Please solve the problems because it becomes difficult. Okay. With the calculations, it becomes difficult. Please solve the problem along with me today, please. I'll share it again. We will solve it in the form of a table. Use a table method only. Okay. So I have pasted the values of x1 and x2, the vectors, as well as the initial weights in the table. Okay. And also written the relevant equations which we are going to use for the calculations. Okay. So for the calculations, since we are going to use bipolar sigmoid, we know that it is tan h of net by 2. So that is what I've written here. And f dash net is half of 1 minus o square. Okay. And this is the weight update equation is given c into d minus o f dash net times x. Right. So let us solve this problem quickly. So what is net for the first training pattern? What is net value?
1.
It is 1. Okay. Others are getting, others are not solving. Is 1 correct? So what is O? Quickly, just run this half over tan h function on your calculator.
0.462.
0.462. Okay. Next is f dash net. Half into 1 minus o square.
0.3933.
3933. What is okay? D is given now. You have to compute this term. C times D minus O times. I told you the trick. First, you compute this and then keep on multiplying by the individual x values one by one. So, I mean, till here you compute C times C is given to be 0.25 D minus O, okay, D minus O times F dash net. Okay. This term you compute and one by one you take the x values and multiply that term with x. It will be faster. This will be 0 because that x2 is 0. Tell me the value for delta W1 and delta W2. So delta W1. What is delta W1?
Minus 0.2876.
delta W3.
0.14375.
Okay. Now next step. What is the next step? I will randomly ask someone. Now Sagar and Harsh have to stop. I will ask someone. What is the next step? Okay. Who's going to answer my question? Yes, Mansi Jadhav. Mansi, are you there? Mansi, are you there? Okay. Neha, are you there? So all those names which I'm calling out, they're not answering. They will be absent for today's lecture. Swati, are you there?
Yes, ma'am. Updating the weights.
Okay. How do you update the weights?
So W1 will be W1 plus delta W1.
Okay. Good. Okay. So tell me the answer. Now the weights are there in front of you. Tell me the answer for W1 plus delta W1.
0.7124.
0.79.
7124.
7124, no? Okay, fine. W3 plus delta W3. Who is answering? Not Swati. Trupti. Trupti, are you there? Those who are not answering is absent. Vidhi, are you there? Vidhi, Ronak, are you there? I will not upload the recordings if you behave like that. Huh? I'll stop uploading the recordings, the lectures. Okay. Whoever is there can answer. W3 plus delta W3. Simple. It is 1 plus 0.1437, right? Next, net. We compute net W transpose X. What is the value for net?
Minus 0.4313.
0.4313. So O is half of that net given to tan H. What is it?
Minus 2124.
Hmm. F dash net.
Zero point 0.4774.
Okay. Delta W1, 2, and 3.
Point 1447.
0.144 is delta W1. and
0.2894.
minus, no? Or plus.
हाँ minus.
And this is also, it's the reverse of that, no? 1 or minus 1. Same way. Okay, and final weights are 0.8. Simple, just add up the W and the delta W values. So 0.85. There is something after 144. Which digit?
7.
Okay, so 7 plus 4, 11. Right? Correct? This is 1437 and this is 1447. So what are you
Point
getting?
triple nine.
Point?
999.
Almost 1. Fine. So these are the final weights, W2. Right? So we will have some punishment for today's lecture. Those who are not answering. Let us move on with the algorithm. Okay, we have already discussed the single discrete perceptron training algorithm. In the lab, I have discussed it. It is just the steps that you have solved, used to solve the problem, put in the form of an algorithm. Okay. So on similar lines, you have the single continuous perceptron training algorithm. Okay. Okay. So what is the algorithm? So you just have your training pairs, that is your data set, which includes the input vector along with the desired output for each of the training pattern that you have. And then what you do is, first step is, before you give it to the network, you have to augment it with the additional input. If you notice previous examples, whatever we have solved, last input is a -1 or a +1. Okay, you can take this as -1 or +1. Okay, so this is the augmented input. Now this augmented input that we have, uh, this is given. So now instead of X, you will have Y given to the network. And then of course you have to choose your learning rate. Okay, and there is one quantity called as the error threshold that you need to select. So when do you stop the training, right? Now in case of the single discrete perceptron training algorithm, you stop the training when the error becomes 0, because that is a discrete neuron. But in this case, since it's a continuous neuron, so you will never get the value as 0. Okay, but it will be a value close to 0, and that will be a threshold that you have to decide. So based on the error value, as close to 0 as possible, 10 raised to -3, 10 raised to -4, 10 raised to -5, that is the range of the error you look at. Okay, depending on what kind of accuracy you want. Okay, we are looking at the error, minimizing the error, squared error. So you compute the squared error at each step along with the actual algorithm. And then at the end of the training cycle, you look at the total error. Okay. So the next steps follow the same way that you solve the problem. That is, W is given. So W is n plus 1 now, cross 1. Okay. You initialize the weights, you form the initial weight vector with small random values. Okay. And then you use start with the training cycle. This is cut for some reason. So you use the activation function, whichever you're deciding, you decide that. So in this case, this is mentioned, what is mentioned here is the bipolar sigmoid. You can use the unipolar sigmoid function as well. So based on that, the weights are updated. So based on this, the weight update equation is learning rate or learning constant times d minus o times f dash of net. In this case, since it is bipolar sigmoid, it is half of 1 minus o square, okay, times y. So this is the weights. Then you compute the cycle error. And then what you do is you do this for all the remaining patterns. So you repeat these steps for all the remaining patterns, right? And then at the end of one epoch or at the end of one iteration, what you do is you check for the error that you have computed. So this Emax is a threshold which you are setting, and E is the error which you are calculating throughout the algorithm. As you're presenting the pattern, you compute the error. Second pattern, compute the error. Third pattern, compute the error, and keep on accumulating that error into E. So what you're going to do is you're going to compare this E with Emax. So at the end of the iteration, you will compare the E with Emax. Now, if E is less than Emax, that means that your training is complete. Your error has reduced below the threshold set. So now that means you will stop the training, whatever threshold you have set. Suppose it is 10 raised to minus 4. So the moment your computed error, cycle error, goes below that, you stop the training and you output as an output of the algorithm. What are you going to output? The weights. The weights and the error is, it's okay, it is, because error you are setting, so it is fine. And at what step? This k is nothing but the step count, how many steps were required to solve the problem. Okay, and once this is done, this is the case when the cycle is complete. I mean, when the error has reduced below the threshold that you have set. And if it is not the case, so if your error, computed cycle error, happens to be greater than the threshold, then you continue with this process. Okay, so you reset the error E to 0, and again you compute the cycle error for the next iteration that you have. Okay? And you start with the first pattern all over again. So 1, 2, 3, 4. Suppose there are 100 patterns. So 100 patterns will give, and after that 100 patterns, again you start with pattern 1. Okay, that is what you do. But this algorithm is for a single continuous perceptron training. So what you need to do is this algorithm actually is going to be extended for a multi-layered network. So for a multi-layered network, this will be extended, and then we will see, I mean, step by step how this is extended. So from a single continuous perceptron, you will have a layered perceptron. So multiple perceptrons, okay, in the final layer. And from that, you will have a multi-layered perceptron. So we will keep on extending this algorithm one by one, because the delta learning rule is used in all these algorithms till we go towards backpropagation. Backpropagation also, the basic rule that is used is delta learning, and it is, I mean, it's all mathematical, lots of derivatives to be multiplied, and that is how you get the final training equation for the backpropagation algorithm. Okay? So the story starts from this algorithm. So that's about SCPTA. Okay. So the next type of learning is Widrow-Hoff learning. Now, what is this Widrow-Hoff learning? Widrow-Hoff learning actually came into picture before the delta learning rule that was conceptualized. Widrow-Hoff, again suggested by Widrow and Hoff, these two scientists. Okay, and it's a very simple learning rule where what happens is the learning rule in this case, the learning signal in this case, is very it's very straightforward. You do not have any kind of a derivative here, and you do not have any kind of an activation function here as well. Okay? So this particular learning rule was used in a network called as Adeline, or adaptive linear element, the long form of it. And it was tested on this kind of a network. So it used all the neurons which were used here. These were using this Widrow learning rule. Okay. It is applicable to supervised training because you require D here. So D is used here as well. And it is independent of any activation function. So how is it independent? Because we do not use any activation function. So the network, the output of the network is basically the weighted linear combination of inputs. So it's simply a weighted sum of inputs. Okay. That means what? It is W transpose X. O is nothing but W transpose X. Okay. So since O is W transpose X, R is D minus O in this case. It is R is D minus O, and O is W transpose X. W transpose X is also called as net, right? Net is nothing but W transpose X. So this is the learning rule. Now this particular rule also, it tries to minimize the squared error between the desired output and the neuron's actual output. Okay. So weight update is C times R times X, right? And this is a single weight adjustment. So if you're talking about the individual weights at that level, what it is, the same thing per element of that X vector. Okay. And this rule actually is a special case of the delta learning rule. So how is it the special case of delta learning rule? In this case, the function f actually, f of W transpose X is actually equal to W transpose X. So what is f of net? F of net is net. So that is why f dash net is 1, right? Since f of net is net, f dash net is 1. So are you getting it? So in that equation, if you substitute f of net as net in the delta learning rule equation, substitute f of net as net, then f dash net will be 1. And you come up with the Widrow learning rule. Okay, so it's a simple learning rule. You do not have to compute any derivatives here. These are some of the older networks which were used. Okay, now they are not used in practice. The delta learning rule is used everywhere, as I told earlier also. But since these were some of the learning rules which were proposed, we have to go through them. That is why we are discussing them. Okay, so if you have to perform this Widrow learning, training using Widrow learning, okay, it will be faster. So I want people to answer. See, I'm going to give a punishment, those who are not answering. Everything is there recorded. So whichever names I'm calling out, they have to answer the question. The table is there for you. X1 is there, X2 is there. The same patterns are the same problem. Only thing is, instead of delta learning, we'll be using Widrow learning. Okay. So now tell me, everything is given in the table, in fact. So O is, now we know O is nothing but net, because we do not have any activation function in case of Widrow learning. Okay. So D is given to you. And we have the weight update equation also given here. C times D minus O times X, right? So you have to answer now. No choice. Right? So net also I have written here. Now just complete this table for me. This is net. So O is net, right? What is delta W? Delta W is C times D minus O times X, right? C is given to be 0.25. D is there with you, O is there with you. Can you tell me the delta W values? Now who is going to answer this equation? The answer, let me see. Rucha, are you there? Rucha, are you there? Okay. Sahil, are you there? Great. Sarthak, are you there? Utkarsh, are you there? Shreya, are you there? Prerna, are you there? Mayur, are you there? So entire class names only I have called out, no? Nikki, are you there? Parth, Ravesh, Rajat.
Yes, sir.
Yes, Rajat. Can you answer this question?
Delta W1 is -1.
Delta W1 is -1, right?
Delta W2 is 0 and delta W3 0.5.
Correct. Good. Okay. Can you tell me the W values, the new weight values?
W1 0,
Right.
W2
This is
0, W3 1.5.
right. Good. Okay. So O is equal to net. So we have net. I have computed it already. Yeah. So now quickly tell me delta W1, 2, and 3. Anyone can tell who is present.
0.625,
0.625
minus 1.25, and
minus 1.
minus 0.625.
Correct. Yeah. So final weights will be
0.625 minus
0.625.
1.25.
So simple to solve the problem. Yes. And this minus this.
0.875.
Very good. So those who are absent today, I mean those whose names I have called out and they did not answer, I don't know. They will still have to look at the recording whether their names were called out. They will have to solve. There's one problem here which they will have to solve and upload on Moodle. That is a punishment. Okay, one problem will be given to you that has to be solved and uploaded on Moodle. The screenshot of it you can put. Whichever names were called out. Okay. This you have to inform to your class. Who can inform to the class? Sagar, you can inform to your class.
Yes, ma'am, I'll do that.
Tell them to listen to the recording and see if the name was called out. All those students have to upload.
Yes, ma'am.
Yes. So the next learning rule that we have is correlation learning. Now, correlation learning is a special case of Hebbian learning. And what happens here is the signal R. In case of Hebbian learning, you know that R is equal to F of W transpose X directly. It is unsupervised. Hebbian learning, the proposed Hebbian learning is in an unsupervised algorithm. Okay, so this is a special case of Hebbian learning where R is equal to D instead of O. So it is a supervised environment which it uses because you have the label with you. So directly R is equal to D. You're moving it, you're guiding the uh, weight update by using the label, the target that you have. Okay, so this is correlation learning. So weight update equation is W plus C times D times X. So R is D here. Okay, C times D times X directly. Okay, so this is one more of the rules that are there. Okay, so this is one problem on correlation learning which you can solve as homework. Okay, so in fact this particular problem has to be uploaded by all those who are absent. Okay, the table is there for you. I will upload these slides, but you have to complete this table and uh, submit it on Moodle. Okay, this is the problem which they have to do. Sagar, you can tell them.
Yes, ma'am.
So I'll stop today's lecture because I want to discuss two more rules. One is winner takes all, and one is the last one is outstar learning rule. These rules actually they work on a layer of neurons rather than a single neuron. So all the rules that we saw so far were working on. We were talking with respect to a single neuron. The weights were we are updating to a single neuron, which are connected to a single neuron. Now, in case of the two remaining rules that we have, they work on an entire layer of neurons. So that layer of neurons that we have, I mean, you don't have single neuron but layer. One of the rules is winner takes all. So winner takes all is a competitive learning rule, which is an unsupervised learning rule. So basically, there is a kind of a competition in this layer of neurons. Okay, and there is one winner which is selected. So it's a competitive learning rule that is there. That is winner takes all. One of these neuron will be selected as the winner. So let's say this, depending on some computation. Okay, we will see how what is the idea behind that. How does it do? Because the rule is unsupervised. It is unsupervised. Winner take all is unsupervised in nature. Okay, so you do not have D with you. The only unsupervised rule that we saw so far was Hebbian, right? Only Hebbian was unsupervised. Rest all were supervised. Now, winner takes all actually that we have, it is unsupervised and it is the basis for clustering that you have. Okay, there's so many clustering algorithms. So winner takes all also is kind of it's a clustering algorithm. It's a learning algorithm. So we will look at this where the n number of neurons compete. They are put into a competition, and one of them wins. Okay. So we will look at this rule in detail, the mathematics behind that, and how do we get the winner. And we have to implement this also. This winner takes all in the lab. Okay. So in the next lecture, we will discuss this winner takes all and one more rule that is there, outstar learning rule. After this, we'll discuss that as well. Okay.
Ma'am, where do we have to upload that question that we solved on Moodle?
So you're back.
Ma'am, I was there, but you did not give the chance to speak. You were taking the name so quickly. You
So
only
where
stopped
were
at
you?
the end. I was here only. जितने में मैंने बोला उतने में आपने दूसरा नाम ले लिया था.
So you should have interrupted, na, if you were there.
तो फिर मुझे लगा आप नेक्स्ट पर्सन को पूछ रहे हो.
You should have interrupted. Everyone will come now and say, "Na, everyone has got the
No, ma'am,
message on
but
the
I'm
group."
just asking. No, I'm just asking where do we have to upload the
I
question?
will
That
put a link. I will put a
yeah.
link on Moodle.
Mm-hmm. Mm-hmm.
There you will have to upload.
Okay, and the deadline will be?
Deadline will be before tomorrow's lecture. I'll put it today only.
All right.
There's this one problem you have to solve.
Oh, that's in the slides, right? Slide number 12, 13.
Yes.
Okay, okay. All right.
We'll stop for today. Continue in next lecture.